So, we continue with lift, right, as we are doing, and this we have looked into, and then we said that we can also simulation is also possible. This becomes important. We are looking at when one is looking at random interflow traffic, rather than we have designed it on the basis of upgoing traffic, right, one way. But there can be situations where random interflow traffic is also there. So, one can simulate it also. Now, basically this is done as a Poisson's process. This is done as a Poisson's process, right. So, it is done as a Poisson's process. So, what we assuming is, first of all, let us say lambda persons per unit time is the rate of arrival. Let us say lambda persons per unit time is the rate of arrival, and lambda t is the person arriving in time t, right. Now, we assume that time interval is very small, delta t, such that not more than one person will arrive during that period of time. It is so small that not more than one person. So, we call it as a success. So, one person arriving during that period of time. So, very small time delta t, and during that period of time only one person can arrive, right. And there are such n number of such trials are there. So, n number of such trials, or n into delta t time I am considering, right. Now, if you look at it, this is a if I look at this is actually a case of a what we call a binomial distribution. That means, I have either success or failure. So, if the probability of success is probability of success, let me call it p, then probability of failure is 1 minus p. Supposing I am interested in finding out of my n trials x success, right. Now, I was just talking about last class, I was talking about scenario of a die. So, supposing I want to find out what is the probability of I have n trials of the die, I throw it n times, and what is the probability that I get x number of times, only 4, any. So, getting probability of getting 4 is success is 1 by 6, because there are 6 outcomes possible, and probability of failure is 1 minus 1 by 6, which is equals to 5 by 6. So, to get exactly x number of success out of n trials, let us say. So, if I have to get x trials, x success, it is basically the joint probability of x success and n minus x failure, because exactly x I want to get. So, probability of x success is 1 by 6 to the power x, and joint probability, so multiply 1 by 5 by 6 to the power n minus x. So, that is the joint probability of, but this x I can select in NCX way. For example, first x can be success, next n minus x can be failure, or maybe the first one itself is a failure. So, I can select. So, therefore, this is what the concept of binomial distribution is, right. So, here also we are applying the same thing. I have got, as I said, I have got n number of trials. So, probability of x success in n trial is given by this formula, right, probability of x success. And when this p is very small and n tends to infinity, p is very small, n tends to infinity, then this is what is a Poisson's approximation, So, when p is probability of one success, so this is what we said binomial is when n tends to infinity, p tends to 0, p is small, you can show by expansion of this one. The mean of course is x p x, the mean would be, how will you write mean? Mean will be x multiplied by the probability of x, sum it up for all the possible outcomes, then you get this value, and this you can show will be equals to n p. So, whatever it is. So, when n tends to infinity, p tends to 0, one can show that this probability is mu to the power x e to the power minus mu divided by factorial x, right. Now, mu itself is equals to n p. So, therefore, one can use this Poisson's distribution concept for simulation of the lift thing also. So, let us look at this. Probability of finding a person in jth floor is Pj by P. Probability of finding a person in jth floor. So, the lift is somewhere, probability of call from jth floor, right. Probability of call from jth floor would be Pj by P, and P is the population, capital P is the population, capital jth floor summation, yeah. So, capital P should be basically total population or summation of all the floor, yes, sigma pi, etc., etc. So, let us say it is the total population, I am calling it as P, total population I am calling as P. So, probability of 0 calls, right, probability of 0 calls from that floor, probability of 0 number of calls or no calls from ith floor to to jth floor is, supposing it is at ith floor, somebody wants to go to the jth floor. So, the probability is the joint probability of basically not joint probability of finding 0 person belonging to jth floor who is making a call from ith floor, probability of finding 0 person making a call. Now, the mean in this case would be, as I said, is equals to n into p, mean is n into p, and in our case, in our case p was equals to p, rate of arrival was, if RT is the round trip time, lambda RT is the number of people coming in during that period of time. So, rate of arrival. So, if you go back to the previous slide for binomial distribution, it's probability of number of people boarding a lift, this is lambda RT, lambda is the rate of arrival, RT is the round trip time. So, total number of people who are going to come during that period of time is lambda RT. Now, if x people have to arrive, x success has to occur, then to the power x, and this is what we said, the mu is basically is equals to mu itself is lambda into RT in this particular case. I hope I have something more than this here, or I have just left it here, not really. So, this is lambda RT is the mean actually, mu to the power x and e to the power lambda RT minus mu divided by x bar. So, that is considering it as a Poisson's process, the probability of x number of people boarding the lift in a cycle at any level is given by lambda RT to the power x into e to the power minus lambda RT divided by factorial x. So, probability of 0 number of calls, that is nobody boarding from that ith floor who will go to the jth floor, is actually the joint probability of finding a person in jth floor, but nobody boarding from ith floor. So, that is why this multiplication 0 person actually pressing for jth floor in ith floor or any floor for that matter, in this case we are saying ith floor. So, this would be simply, this is 1 and this is e to the power lambda RT Pj by P. So, that is the probability of finding no person at any floor pressing for jth floor, pressing for jth floor, right. This is a kind of concept we are using. P by Pj by P is the probability of finding a person at jth floor, 1 minus RT is the probability of at least one passenger boarding. So, this is the probability of finding 0 person calling for going to jth floor. 1 minus that would be at least one person pressing the button to go to the jth floor. So, is the probability of at least one passenger boarding at any floor. So, if it is ground floor, it could be ground floor lobby, and who will disembark at jth floor. This I can extend to any floor. I am saying ground floor because if we look at one way traffic only, upgoing traffic only, then this will be at the ground floor. So, at least one person boarding the lift to go to jth floor will be given by 1 minus e to the power lambda minus RT into Pj by this 1 minus this term, right. Thus, expected number of stops one can then find out. So, expected number of stops will be like we did earlier. This is for the first floor, this is for the second floor, this is for the third, all the n terms if I multiply, then I get expected number of floors, because P1, this is probability of finding at the first floor, this probability of finding at the third floor. This, if I find one person, at least one person, then multiplied by 1, that is one number of stop. This multiplied by again 1, finding one number of stop. I mean stopping at first floor, that means one probable stop. Probability of stopping at expected value is a one stop at every floor. So, 1 multiplied by the probability of stopping at that floor. So, probability of stopping at first floor, second floor, third floor, and everyone I should be multiplying by 1. So, this is this n terms I should sum up, and if I sum up n terms, I get this sum, there will be n such terms of 1, I get n, and this I can sum up as I equals to 1 to n, because n is the total number of floors served, e to the power lambda RT, this term, and this would be P j going from P where or P I going from this will go from P j going from 1 to n. For all of them I should sum it up, for all of them I should sum it up. So, that is the probable number of stops if we are calculating on the basis of Poisson's process, probable number of stops. Formula remains same, RT is the same, by definition it is same, except that only thing we are changing here, we are assuming it to be a Poisson's process rather than a heuristic way by which we calculated the expected number of stops or floor of reversal, that we calculated in a, or rather formulated in a heuristic way. Here we are using it as a Poisson's process, right. Well, they do not necessarily give you exactly the same answer, but this becomes useful if you are simulating it. Now, if you want to find out now floor of reversal, I want to find out floor of reversal, jth floor being the floor of reversal, right, like we did last time. It is the joint probability of finding, joint probability of not finding any person in nth floor, n minus 1th floor, n minus jth floor, etc., up to one floor above, up to one floor above. So, it is the joint probability of, so this was probability of not finding a person going to nth floor, this is the probability of not finding a person in n minus 1th floor, and so on up to the n minus, there is a topmost floor, next topmost floor, and one floor above jth floor. This is not finding one floor above jth floor. So, this is P j stands for probability of not finding anybody above jth floor, probability of not finding anybody above jth floor, because this is probability of not finding anybody in nth floor, this is probability of not finding in n minus 1th floor, that is the one floor just below the top floor, and so on up to one floor above jth floor. So, this is the probability of not finding any person above jth floor. This multiplied by j is the probability of jth floor being the floor of reversal, right, and sum it up for all the floors, then you will get expected floor of reversal. So, that is what we do. So, you see this is product, this is product, this is product, basically this is product, this is product. So, product from product going from n j minus 1 to n e to the power etc., minus this gives me the probability of finding at least one person in the jth floor, like we did earlier. You see, this is not finding up to n minus probability of not finding anybody from one floor above jth floor, and this is the probability of finding probability of not finding anybody one floor below jth floor, but that is the probability of finding at least one person in jth floor, when it will become floor of reversal. You don't find anybody above, you need not find anybody below. So this is what this is what the probability is. This multiplied by j and sum it up for all n of them, then you will get the. So then sum it up for all n of them, then you will get the expected floor of reversal, like we did earlier. Now this is, if it becomes important if you are simulating, you can assume Poisson's process and simulate, so that generate random number, and then even random interflow traffic you can use this concept. If we calculate by this formula, or the heuristic, they don't exactly give you the same. In fact, heuristic one gives you a better answer if I look at for only one directional traffic. So we would be mostly using the earlier one for our design purposes, but I thought I will give you this concept as well for simulation if there is for random interflow traffic. So therefore, okay, so probability of any lift passenger boarding at ground floor lobby not disembarking to floor above nth floor is 1, as maximum number of floor above ground floor is n. So this is floor of, if the floor of reversal, this probability of lift passenger boarding at ground floor lobby not disembarking to a floor above nth floor is 1, because there is nothing above n, and there is no floor above the ground floor. This is the probability of that floor of reversal is nth floor or below. The probability of nth floor being the floor of reversal is the probability that floor of reversal is at most nth floor minus the floor of reversal being at most n minus 1th floor. I am just, whatever I said, I am just putting in the algebraic terms now. So probability of nth floor being floor of reversal is this. If you have any other floor, it will be something like this. So H would be simply j multiplied by Pj, where Pj is the probability of finding jth floor being the floor of reversal. So this is the sum total for all floors. Pn is this, n minus 1 is that same formula that I just mentioned, joint probability and all that, whatever we have mentioned earlier. We are calculating from this product we are calculating from this product. So expanding this, putting it here in the formula overall. So H becomes n into probability of finding nth floor or below, as finding at least one person in the nth floor. So floor of reversal being n, this floor of reversal being n minus 1, n minus 2, n minus 3, etc., etc. So this sum total gives you, because what was this? This is the probability of probability of finding one person, finding what was this? This, just let me repeat, probability of finding one person in n minus nth floor. This is finding at least one person in n minus 1th floor. So summation, this different, n minus, I mean the floor of reversal being n minus 1 is given by this difference, like we did earlier in case of heuristic as well. Same thing, at least one person would be there up to nth floor. One person would be there up to nth floor, and this I repeat. So this pi, that multiplication sign, I am using it expanded form here in this one. So this is in this expanded form. I am just using this in expanded form, and that is how it is. So one can obtain H value something like this. H can be formulated in this manner. H can be formulated in this manner, where n, because this n into 1 will remain. This product again will cancel out, leaving one term, because there is n minus 1 term of this, there is n term of this. So one term will remain, one term remains. Similarly, one term of this one remains, one term of every one remains, and then this is a summation, this summation plus sign here, and this is a product sign, product going from, like earlier also we did the same thing, 1 to n, j going from 1 to n, and this goes from n equals to j minus 1 to n. If this product, if I take, this is the product part, the summation part, every time only one term of this one remains. only one term of this one remains and only one term of this remains. So, this can be, I can sum it up. So, height of reversal, expected height of reversal, I can calculate out in this manner. So, as I said that this does not give you exactly same answer as the heuristic, and heuristic gives you a better answer. You know, heuristic design is better, it is generally better, and if you assume that there is rate of arrival is not same as rate of going up, then we did an trial and error procedure, that way you can find out. So, you can actually design the number of, you know, what is a, like basically if you know what is the handling capacity desirable and how many number of lifts are required, because based on handling capacity, acceptable waiting interval, handling capacity, if you remember, it was the peak 5 minutes period, number of people that will be handled by the lift system expressed as percentage of the total population. So, what we know is waiting interval from there. We can calculate out the waiting interval, and what is waiting interval? Round trip time divided by number of lifts, round trip time divided by number of lifts. So, if I calculate out the waiting interval and I assume a lift capacity, I can find out the round trip time and then find out for the waiting interval how many number of lifts I require. So, basic idea is the number of lifts, how many number of lifts I should provide, lift arrangement and operation of the lift, whether it will act as passenger or it will act as, you know, express, etc., etc. So, scheduling of the lift operation, that is what we said, and this will also this will govern the round trip time. So, it will be related to the round trip time, right. So, basically arrangement is other aspect, design so far we have looked. Just let me reiterate, handling capacity was Q, right, Q is the total number. So, into 300 number of trips will be round trip time divided by waiting interval. Round trip, how many, you know, in each trip will be, if the RT is the round trip time, sometime I might have used RTT, whatever it is, or RT is the notation I might use. So, if RT is the round trip time, RT divided by T is the number of trips, right, because waiting interval is this. So, this is the number of trip during number of trip, right. In number of trips you will have in how many seconds, and 300 seconds you will have this much number of trip actually. 300 seconds, sorry this, yeah, 300 divided by T is the number of trips in 5 minutes. Q is the number of people going in one trip, right, and right, into x multiplied by 100. So, that is it, and T I can find out as RT divided by number of lifts is equals to T, RT, you know, T. So, if I know this handling capacity, if I also know a desirable waiting interval, right, desirable waiting interval, or you find out actually what is the for handling capacity, what for choosing a particular lift size, what should be value of T. So, if you know the value of T, and it should be of course acceptable values, I will just give you that value as well. So, number of lift actually you can calculate out, because T RT divided by number of lifts. So, for given known Q you can find out RT, and RT divided by number of lifts, that should be equals to T. So, on this basis you can find out actually number of lifts. Other thing that you have to do is the arrangement of the lift, right. So, arrangement should be such that passengers can see all the lifts. So, number, type and size of the lift, position of lift well, this is what we got to decide. Particulars of lift well enclosure, size, position, number of landing doors, dimension of the machine room available, this will be available from manufacturer's guideline. So, basically we want to decide number of lift. Type of lift will depend upon occupancy type, because hospital lifts are designed for taking the passengers, so their dimensions are different, right, and normal office lift etc., they are different. Size of the lift of course is Q. Then position of the well depends upon the, as I said, there can be, I can do horizontal zoning, so it's a part of the planning itself. Usually it would be at the central point, at the central core. In a tall building it will be in the central core, because that also helps, and structurally also that might help, or one may take advantage of that. So size we have talked about, number of type of landing doors, that also we can decide how many landings would, like what kind of landing doors you might have. Machine room dimensions are available from manufacturer's data. These are given in National Building Code, these are given in. So only aspect remains is to find out the number of lifts and capacity for a given capacity, and desirable waiting interval for also handling capacity. You should see that what good is. For example, 10 to 15% is for divergent office. Good handling capacity suggested is 10 to 15% for divergent office, 15 to 20% for single purpose office. So what we talked about, the design that is the most complex design is single purpose office. There you should be able to handle more number of people. So 10 to 25% for single purpose, 7.5% is the suggested value in code for residential, because residential people do not go at same time. It's all they at any different time they will go, and remember, number of persons per unit floor area is much less. If you remember, 12.5 meter square per person, while in an assembly office it will be much less area per person. So in residential area population density is less, so therefore this is the handling capacity. And number of floor and speeds up to 4 to 5 floors, these speeds are good enough, right. Above 22.5 meter per second and such speed. Now supposing something like a 40-story building, and you want to go above, let us say 32 story and above. 32 story means, let us say, even if I take it around 32 into 3.5, let us say, or 3 meters or 3.5 meters, So how much it would be? Somewhere around 100 plus, right? 112 meter, right? 112 meters. Now 32 story, 112 meters, and if it is something like 3 meters per second, it will take about, it will take about 30 seconds or so. So that's desirable, that's understandable, it's fine. 30 seconds people will not, but if it takes about 5-6 minutes, people will get actually disturbed. So you can plan that way, that it doesn't stop anywhere, it goes straight away up to the 32nd floor, and then of course it goes as passenger, that's fine. So that's why the speeds are something of this order, speeds are of this order, and handling capacity I have given. Waiting interval, quality of service, acceptable waiting interval 25 to 25 seconds, excellent. 30 to 35 seconds good, 30 to 40 seconds fair, 45 seconds unsatisfactory. For residential building, of course, longer intervals are allowed, longer intervals are allowed. So that's how it is. Escalators, if you look at it, they are used where you have large number of people, but the height you have to serve, service height. I mean, you go from floor to floor, one floor to second floor, that's it. Or maybe, like, then you have to have for each floor or each one level to only for one level you serve. Even if you serve 2 level, because the stop, there are no intermediate stop, it simply goes, starts, goes down, or starts at the bottom, goes up. So basically it is serving one level only, but it can handle very large number of people because it's a continuous process. So they are used for large number of people is to be transferred over a short period of time, railway station, airports and so on. It works at a constant speed and serves only 2 levels. Space required is also large. So but then where you want people do not, people have to go from one level to another only, and you want them to see the surrounding, like in a departmental store or something like that, showroom, then escalators are good, right. 30 something of the order of around, it will handle something like 33,000 to 6,400, 3,200 to 6,400 persons per hour. So handle very large number of people. Angle of inclination is never greater than 30, maximum 35. Angle of inclination is not, it has to be limited. So therefore it consumes quite a bit of space, because this inclination, so it consumes that space, right, and not more than 6 meter height. So this is maximum 6 meter, this is less than 30, this is less than 6 meter. So that's what it is. And width usually 62, widths of this kind, tread comfortable should be less than 42, rise not more than 22. Capacity, generally this is a simple formula. If the width is, W is the width, right, between the handles actually. So 2.7 W into A, where A is a horizontal distance between horizontal comb plate and teeth, because it goes as a steps. When it returns as a flat one at the bottom side, which you do not see. So it is related to that. Rated speed not more than 38 meter per second, it should be 3.8 meter per second or whatever it is. And W, so one can calculate out the capacity using this formula 2.7 W into A, right. So one can calculate. So that's basically escalators. So escalators are more or less standard design. There is nothing to be done. You got to plan for it, that okay, this is the place I put it here, and where you are only you choose them where you have large number of population to be handled. I think we will break, and if you have any question, we will take that.